Hello. So we're continuing talking about inverses, and what do we learn from our last video? If two functions are inverses of each other, there's really an algebraic way to verify that, and you have to show compositions in both directions that they equal x. F of g of x has to result in x, and g of f of x has to result in x. So what happens is the reason why is because f is, of course, receiving g of x. So when x goes into g entangles x, it entangles the domain, and it produces a range element. And then f's job is to take that range element and untangle it and give you back your original x value. So doing composition here shows that f will undo g, but you also have to show that g can also undo f. So you can think of it that way, but also remember composition is not commutative, so you have to do it both ways anyway to show that they both result in x, your original domain. Now, how do you even find the inverse of a function? That process, you switch the x and the y and you solve for y. And when two inverses are graphed, they will be symmetrical about the line y equals x, and the domain of one function will be the range of the other. And it really doesn't matter if they're both inverses of each other. If f is the inverse of g, then guess what? G is the inverse of f. Okay, now these two functions here happen to be inverses of each other. One reason that we can prove that is just graphically. Every ordered pair on the green function, if you switch its domain and range, you will get every ordered pair on the purple function. And that is the key characteristic of inverse functions. For example, 0, 5 is an ordered pair in the green function right here. But then if you switch the domain and the range, you get 5, 0, which is on the purple function. Negative 2, 1 is on the green function right here. And if you switch the domain and the range, you get 1, 2, which is on the purple function. Same thing with negative 4, negative 3 gives you negative 3, negative 4. Now, negative 5 happens to be on the green function and the purple function. So I don't need a second order pair. It's on both of them. And notice the domain equals the range, or in other words, the y equals the x. That's a consequence of being precisely on the line of symmetry. The line of symmetry is y equals x. So as you can see, the green and the purple functions are symmetrical about that line exactly. And every point on that line, of course, the y equals the x. That's exactly what it's saying. Now, this is a function. This is a quadratic function, which is y equals x squared. But notice y equals x squared is that the vertex is at 0, 0. This one got dropped down 5 units. So this is the function x squared minus 5 transformations. That's section 2.5. Now, you all know the vertical line test. You draw or you think about every possible vertical line, and if it hits the relation once at a max, then that relation happens to be a function because one x value will produce one y value, and every vertical line represents a different x value. But there's something called a horizontal line test. And here, same rule, if a horizontal line hits the relationship in two different ways, it fails something else. And for us, or for mathematically, what it fails is the existence of an inverse. This quadratic is a function, to be sure, but it fails what we call the horizontal line test. And so that means that this function does not have an inverse. All right, that means nothing if you don't know really what an inverse is. Why is there such a thing as the horizontal line test? Well, here it is very quickly. Let's go back to the vertical line. Every vertical line is an x value. Well, here, when x is 2, the product is negative 1. The function produces negative 1 when x is 2. So that would make you think that if this function had an inverse, if I give that function -1, it should bring me back to +2, like switching the domain and the range. But x equals -2 also produces -1 as a y value. So that's a problem, because if I give the inverse -1, what x value is it going to give me back? What value is it going to return to me? Is it going to be give me back -2, or is it going to give me back +2? It can't give me back both, because if you have one input giving out two different outputs, then that thing is not a function anymore. So that is why the horizontal line test exists. Like here, the horizontal line, this is when y equals -1. And since it hits the relationship in two different spots, there are two different x values that produce y equals -1. So if you were to reverse that, which x value would you want to go to? 2 or -2? Or for instance, way up here, 3 or -3? So since it's going to two different outputs, it's not a function. So if it fails a horizontal line test, it doesn't have an inverse. But if it passes the horizontal line test, then it does have an inverse. And we call those functions one-to-one, because one x value will produce one y value, and reverse, one y value will produce one x value. All right. So here we have a function g with a domain of -8 to infinity. We knew that already because it's a square root function and you can't take the square root of negatives. So all the x values have to be -8 or greater. And we're told that g is one-to-one. That means it has an inverse. And we find the inverse and also find its domain. So let's do some algebra. So remember that big algorithm, how do we find the inverse? We'll replace g of x with y. We'll switch y and x, and then we'll solve for y. So I would add 4. How do I get rid of that radical? You would square and then subtract 8. And then voila, this is the inverse function. Now this is a quadratic. Normally quadratics have a domain of all real numbers, but not this quadratic. We have to restrict this domain because this quadratic is acting as the inverse of this function. So we're going to restrict the domain. So that's the last piece of the puzzle for this problem. How do we find this domain? Well, remember, as soon as we switched x and y, we switched domain and range. So if we could just figure out the range of this, it'll be the domain of this. We were told the domain is -8 to infinity, but what's the range? You have to know the tiniest amount about the behavior of radicals to figure out what the range is. Square roots will only produce what? They will only produce non-negative numbers. There's no situation on earth where you're going to take the square root of something and end up getting -3. That's not going to happen. You either take the square root of something and you get a number, a positive number, or you take the square root of 0 and you get 0. You're not going to take the square root of something and get -3 or -4. That just doesn't happen. So the square root here will only produce values beginning at 0 and rising up to infinity. So that's the range of all square root functions. But then this -4 shifts everything down 4 units, including the range. So the range was sitting at 0 to infinity, but when you shift everything down 4 units, all the range values go down with it. So now the range is from -4 to infinity. And the range of this function is the domain of the other. And the domain of one function is the range of the other. That always happens with inverse relationships. Because another point to make here is that it's the undoing part. G will take any number in this interval and produce any number in this interval. Okay, now what does the inverse do? Well, the inverse must take any number from here and put it back to any number in here. So domain, range. Okay, I want to graph those two just to really drive home the idea of symmetry. So here is the graph of the square root of x plus 8 minus 4. Notice the domain, or the shifts rather. You shift it to the left 8 and down 4. So the domain is everything from negative 8 beyond, and the range is from negative 4 and up. The other function, the inverse, was x plus 4 squared minus 8. Now that is a parabola, and this red parabola, of course parabolas have a domain of all real, but we had to restrict this parabola's domain so that it behaves as an inverse of this square root function. And we've discovered that it was every x value that's greater than or equal to negative 4. Now, I don't know how to do the or equal to part, so that doesn't matter right now. But so here's that parabola that's only existing for x values at beginning at negative 4 and moving towards infinity. And here is a relationship of these two functions, and they are absolutely inverses of each other. If you flip all the x, y's on the black one, you'll get the red one. And furthermore, if you graph y equals x, of course, they're symmetrical. Okay, this function, two more examples to go. This is definitely one worth your time because there's a little bit of a challenge to solve for y here. So we have to find the inverse of this one-to-one function. Okay, it's one-to-one, which means it passes the horizontal line test, but most importantly, it has an inverse, and we're going to find the inverse. Notice the domain is kind of attached to this function. X cannot equal negative 2. Of course, that's an easy one because that would make you divide by 0. So x cannot equal negative 2. If you were to graph this, there would be a vertical asymptote at x equals negative 2. I want to find the inverse. So we go through the process. We replace f of x with y, and then we switch x's and y's. As soon as we switch x and y, we found the inverse. This is the inverse. We always express it in terms of x, so we had to solve for y. So how am I going to solve for y? Well, we have a fraction. We get rid of the fraction typically. So multiply both sides by y plus 2. And on the right side, the y plus 2's cancel out. So on the right side, you would have 3y minus 1. On the left side, it's x times y plus 2. Here you distribute because you're mixing multiplication with addition. And then this is where a lot of students get. And then they either stop or they break the rules. So how do we continue here? We have to solve for y. The problem is that there are two terms that have a y, but they're not like terms. So any chance of me combining them is out the window. How are you going to get y by itself? Well, you might be able to get the first step without even knowing how to do the next step. But the first step is sensible enough. Let's get all the y's together as much as we can. This term has a y and this term has a y. Let's get those on the same side of the equal sign and get rid of the term that doesn't have a y. So I'm going to subtract 2x and I'm going to subtract 3y. But then now what? And here's the breakthrough. We could factor out a y right here. So try to imagine if you factor out a y, you'll be left with y times x minus 3, and then you could divide both sides by x minus 3. So that's what we do. We factor out a y, and then we're one step away. You just divide by x minus 3, and that is the inverse. Now, when you divide, you have to be sensitive to division by 0. That's a big one. So you divided by x minus 3. Isn't it possible that you divided by 0? It's only possible if x equals 3. Way back up here, we just know that x doesn't equal negative 2. It doesn't say anything about x not equaling 3. So we have to add that. We have to say x cannot equal 3 for this relationship, which is the inverse. The inverse is negative 1 minus 2x over x minus 3. And then the domain is all values except for positive 3. I rewrote this as this. These two things are the same. This looks a little bit cleaner. You usually try to avoid negatives if you can. So what I did was in the numerator, I factored out a negative 1. And in the denominator, I factored out a negative 1. And then those two negative ones canceled out. So notice the top became all positive because I took out a negative from both. And then the bottom switched signs. -3 became +3. X became -x. Last one. Graph the inverse, if that's even possible, of the function graphed below. Now, these are both functions. For sure, they're functions. But the function on the left doesn't pass the horizontal line test. It fails here. It fails. So that means that there are two x values that produce the same y value. So if you reverse that, you wouldn't have a function anymore. You would have one input producing two outputs. So this function doesn't have an inverse. That's a function. So we will not bother with that. The function on the right does pass the horizontal line test. So it is 1-to-1, which means it has an inverse. And how do we find it? Well, we have to graph it, which means we just have to find ordered pairs and then reverse them and plot those new ordered pairs. And that will be that. So my first ordered pair, I see 9, 4 is an ordered pair. 9, 4. If I flip that around, I would get 4, 9. So over 4 and up 9, well, that's off my graph. So I won't graph that. I also see 6, +2. 6, +2 is a ordered pair. If I flip that around, I get 2, +6. So that one I could squeeze in. Another ordered pair is this, 3, 0. Well, if I reverse 3, 0, I would get 0, 3, the y-intercept. Another one is 0, -2. That's the y-intercept on the red. 0, -2. If I flip that, I get -2, 0, the x-intercept on the inverse. Another one is this, -3, -4. Well, if I flip that around, I would get -4, -3. And those are all the ordered pairs that I could see that are integers, and that's good enough. I've got a line, its inverse is a line, so I just connect the dots with a line. And I can extend this, but this black function is the inverse of the red function, and please notice that it is symmetrical to the line y = x. All right, good luck, everybody.